So when you have any system at all, where you have an input, you can call the input x of t, it really doesn't matter. And you have an output y of t, and you have some, and this is a linear time invariant system right here. You can't do this with a nonlinear system. So you know the general way, that if you saw this diagram, just if that h of t implied the impulse response, you know that y of t is actually x of t convolved with h of t, or it's equal to the integral from minus infinity to infinity, or over where pulses exist. It can be of x of lambda times h of t minus lambda d lambda, or you can write this as the integral from minus infinity to infinity of x of t minus lambda times h of the lambda d lambda. And the order is unimportant. It doesn't matter if x is first and h is second. It really is no consequence because they're multiplied. Now that is basic linear systems. That's in the time domain. In the frequency domain, you all know it'll be like x of omega, and over here it'll go in and it'll be an h of omega, and the output here, y of omega, will be equal to h of omega times x of omega. Either one of these in the frequency or time works. The way I'm going to do the matched filters in the time domain. So the whole idea is with a matched filter, you want to maximize something called a signal to noise ratio, or SNR. Ratio. And that's simply either the power or the energy in the signal divided by the power or energy in the noise. And when they do this, there's a lot of ways to do this, so it's really, I'll put this, energy in signal divided by energy in noise. Now, almost always, when you're talking about noise, you're talking about naturally occurring sources of noise or things that you can't eliminate. And they are called wideband. So just to be sure about this, if you looked at the spectral energy density of noise, and I know that there are sources of noise that actually do have an autocorrelation function that is not an impulse. It only occurs at basically the time equals zero. It's the only time there's any correlation at all. The spectral energy density of these things, almost always, with very few exceptions, if you look in the frequency domain, it would be flat. And the value of this is NO over 2. And it's really, the units of this, which is a good question, is volts squared per radian or hertz, depending on if it's in the frequency or omega domain. That's it. So you get the idea. Noise is wideband. It's everywhere. You can't get rid of it. By the way, this is a side note, but I think I talked in here about an impulse has, in the frequency domain, an infinite, matter of fact, it's kind of nice to actually talk about this. You know, an impulse function of t has actually a spectral density of 1, and you can think about it as an impulse function of tau could be an autocorrelation function of noise. And that would cause the frequency domain content to be just constant 1. Now, if, you see it's a delta t there, y'all follow me on this? It's the only time there's any correlation, because there's absolutely no correlation between noise at t equals 0 and noise at t equals any other value. The average value of those are 0. You with me on this, class? At least get the idea. So if that's the case, this would be the spectral energy density of noise. And you can go ahead and put a constant K here. And that K would be associated with an NO over 2. The only reason the 2 is there, the over 2, is because it's got positive and negative components. Do y'all follow me in this class? Omega has positive and negative components. So they call the noise power NO over 2. This is the signal to noise ratio, and it's critical. So now, what they normally do is say this. If we have an input X of t and an output Y of t like this, they're going to say, if you talk about the energy in the signal, and I'm going to put it this way. Right here. Well, you're going to take, and this is the energy in the signal in the output, by the way, of the system. That energy in the signal will be equal to really this value y of t. This would be the energy at t, by the way, so I should put it this way, squared, or it would be equal to the integral from minus infinity to infinity of, and yeah, I'll use this one, x of t minus lambda times h of lambda d lambda squared. That's the energy in the signal, and the only thing you're doing is taking the output value. Now I've got to be careful about this. I'm talking about the energy in the signal at a time t, and in the book he'll talk about t naught, and this is going to be something, I'll just try to, I'm trying to get through this part because this is not essential, but it should give you at least an understanding. Whenever you're talking about signal to noise ratio of anything that's got a finite duration, an energy signal, not a power signal. Power is a little different, but it's, in essence, it's the same thing. But when you have an energy signal, like we're going to be talking about, a radar pulse, for instance, it has a finite duration, it's launched, it hits something and it comes back. When you have that, and you want to take a look at the ratio or the signal to noise ratio of like a reflected return, you always have to talk about it at a point in time, because the signal to noise ratio is 0 if the signal hasn't reflected back. Y'all follow me on this? You have to have some return, and then within that overlap of the return, when the return gets there, there's going to be a point where you'll talk about the maximum amount of energy to noise. That's the idea of this. All right, so this is going to be at a given instant in time. I don't like putting it here because it gives you a false impression because t is continuous. I'll just leave it as t here. Now the signal power is something for this system. If you put in noise, for instance, noise here, I'll call it, here's signal, and if you add noise to it, it's just additive, it would be NO over 2 delta of T would be the autocorrelation. Do y'all follow me on this, class? Because the noise is basically only correlated when there is no time difference between the 2 points. You with me? You can use tau if you want, but it doesn't matter. It's going to go into this linear system. When it goes in the linear system and you convolve it, the y of t here is really going to be just NO over 2 and be the integral from minus infinity to infinity of h of lambda d lambda, because the noise it's an impulse. It only is going to occur at t equals 0. Can you follow me on that one? Now, long story short, that means if this is the actual signal power, if I divide that by the noise power, noise power, which would be h of lambda squared minus infinity to infinity. A lot of times what they'll do is go from 0 to infinity. And the reason is they kind of imply that they don't worry about negative values of time. These are events that you can actually schedule and watch, so negative time doesn't help you, it don't hurt you. It makes it more complicated. And then it'll be d lambda. So, I want to be honest with you. The proof in the book and the way I'm doing it is not the normal way. You usually do this in the frequency domain, because there's one thing that I said here that should at least irritate you. If you put this function into this correlation function right here, you're correlating a delta function that would have t minus lambda, and that means you will get this result eventually right there, but you're going to have to do some mathematical gymnastics to get it down to that point. In the frequency domain, it's easy because you just take h of omega times n naught over 2 and integrate that 1 over 2 pi, the integral of that thing over all frequencies. But it gives you the same result nonetheless. I'm going to stick with this one. So I'm not trying to just ramble on here, but I'm trying to show you one thing. This is the key thing. So the signal to noise ratio is ultimately going to be equal to this, which is, I'll go from 0 to infinity of x of t minus lambda, and it's going to be that times h of lambda, d lambda, the whole thing squared, and then it's divided by that thing, which is NO over 2, the noise power, integral from 0 to infinity of h squared of lambda d lambda. So they get another marker. Okay. How many have heard of the Schwartz inequality here? Anybody? You have? Mm-hmm. I don't know if you remember it, but Schwartz inequality says this in a nutshell. It says if you have an integral of, call it x of tau times h of tau d tau, and go from A to B, I think the way the actual, and it's squared. This right here will be less than or equal to the integral from A to B of the first function, x of tau d tau squared times the second function from A to B, where you're breaking up that integral into h of lambda squared d lambda, or I mean d tau, pardon me, and it would be this squared. So the only thing it's doing is say, if you have two functions multiplied together and you integrate it over range, then you can basically say this value is going to be less than or equal to the integral of the first function just over that range squared, plus times the second function over that range squared. And by the way, the whole thing is squared. That's a Schwartz inequality, and it's in the book. He mentions it. Here's why it's so important. A lot of times, this integral right here is very complicated. In the general form, has no closed solutions. Whereas you can break it into that, and then the argument goes something like this. If you want to maximize the signal-to-noise ratio, since this is the signal-to-noise ratio, right? You know, if you instead of doing this integral, you do this integral, you can say, if in fact this integral right here is broken down to that is maximum, you make the argument the signal-to-noise ratio defined as using this will be maximum too. It's something like that, but you got to follow me. The inequalities help you solve it. That's the only thing Schwartz inequality does. And you'll notice it's equal to or less than. That's the key. So back to this thing, and let me do it. The signal-to-noise ratio here is equal to, and here's where you break this up. You take this and you put it out in front, you get 2 over NO. And then here, I'm going to get the integral from 0 to infinity of h of lambda squared d lambda, and it's going to be times the integral from 0 to infinity of x of t minus lambda, and this is going to be squared right there, d lambda, And I have to divide this whole thing. Now here's what I'm doing. I'm going to retain this in the denominator, but I inverted that, and then I get this. So it's times integral from 0 to infinity of h squared of lambda d lambda. And I'm using the Schwarz inequality. So this is, you may not understand all the details of it. I'd prefer to do this in the frequency domain, but I'm doing it according to what he has in his book, because I want to make sure if you look there, you'll see the consistency. And please write down that page, because it'll help you with some of the problems. This is on page 397. But now, when you take a look at this, what you're going to see is this term and this term cancel right here. Y'all follow me? That's going to cancel, and you retain this. And that right there, when you take x squared and you integrate it over all possible values of x, or over the time or lambda domain in this case, you get the signal energy. Make sense to everybody? All right, so you still say, well, you didn't say anything about the actual concept of the filter. And that's true, I didn't yet, but I'm about to. So now, I gotta say this. That's the input right there, but this right here was the output, y of t squared. And now, and because of this relationship where I can interchange these things back and forth, bless you.
Thank you.
What will actually happen is that it's not super clear doing this in the time domain, but what will happen is this, at least I don't see it. If h of t is equal to the actual input signal x, but then it's going to be reversed in time, and it'll be some value, call it t, minus the actual value of t times k. If that is h of t, you have to have the input signal, and you time reverse it, and that's just a scale factor k. This h of t, I guess you could prove this too if you put it in there. That'd be h of lambda. Yeah, then you would end up getting that x squared, which is the signal energy. I'm just going to say this. I'll get to the point in a second. If you follow this thought, look up here for 1 second. If I replace this, h of lambda, right there, I mean, this would be h of lambda. I know I've got a t in here, but the argument lambda would replace it. Then it would be the time reversal of the actual input signal, the x of minus t with the constant capital T placed in there. Let me just see if I can make this point. You don't need to write this down. Try to appreciate what I'm about to show you. Try to show you at least. So, go back up here for a second and follow me on this one. We already know this thing right here would cancel when we rip it apart, but upstairs, if you do this right, you're going to get the integral from 0 to infinity, and if that's h of t right there, then you get k times x of t minus lambda times x of capital T minus lambda, or I'm sorry, this is actually going to be it's t minus lambda. And yeah, it is minus lambda. And it would be d lambda squared. And then you're still going to have the NO over 2 integral from 0 to infinity of h squared, which would be that signal. I guess if you take a look at this, these two things, if you let small t equal capital T, then these two things are exactly the same, and you're really taking k times x squared d lambda over the entire range, which is the total energy in the input signal. It may not mean a lot to you yet, but that's saying that by doing that time reversal, you get the most possible energy from the input signal to the output. There's this factor here, which is going to be the h of, it's basically going to be the square of this, your lambda. And at the end of the day, you'll find out that the k's will cancel. And ultimately, that's going to be the maximum signal-noise ratio, but it's not real apparent the way I'm doing it here. In the frequency domain, it is. Here's the essence of everything I've just said. In order to maximize signal-to-noise, get back to this thing, of any system, here's what you have to have. And I'm going to give you a visual on it so you understand what's really going on. If I have any process going to the input, and you can say if I have my x of t here, and I'll make it real simple. I'm going to say this is what x of t is going to look like. From 0 to capital T, it looks like this. And you can say it just has a height of a. Now the units of that are usually volts. And they always, if you want to think of it in terms of true power terms, assume the resistance is 1 ohm. So the power would be volts, or power density, V squared over R. If R is 1, is just V squared. You all follow me on this class? Anyway, that doesn't matter. This is x of t here. And I want to look what h of t would be used for the matched filter to get the maximum signal to noise ratio. Then my h of t here would be a time reversal of this. So it's basically going to be x of minus t, but there would be a capital, or there would be a value, I'll use capital T here, minus t here. Now, I'll show you what I mean by that. So the h of t, if I showed you that right here and plotted it, the only thing I'm doing is I take that signal, and if you want to think about it this way, if we let t equal 0 for now, the capital T, then it looks like this. And as capital T starts increasing in value, the only thing you're doing is this becomes T, this is versus, and this, or I'm sorry, this is going to be T, and this is going to be T minus cap T here, where the total width of this remains cap T. And then you're going to go ahead and convolve those things. You with me, class? Just bear with me, and I'll show you how come you'll be able to see it. So the only thing you do, if you want to do a matched filter, you take the input signal, whatever it is, you flip it, right, just like you with convolution, and then you start shifting it through. Here's where it should be clear to you, and I'll give you some examples so you don't have to just listen on words. You actually see something. Erase all of it. So here's x of t. We're going to do the convolution of these two signals. We're going to say, let y of t here be equal to h of t convolved with x of t for the matched filter. So this is my output. Here, you've got to start somewhere, so I'm going to take the x of t and just leave it alone. This is what I propose my x of t looks like. Height A, this is x, and not t anymore, but lambda, x of lambda. Now below it, I take this pulse and I flip it, and then I shift it. So this one is going to look like, and I'll use small t here because you're used to seeing this. It's still versus lambda, and this is basically x of t minus lambda. Y'all follow me on this? You basically have height A. You take this signal, flip it on the other side, and then you're going to actually move it by, I mean the width is cap t, but you're going to move it by a small t value. Y'all follow me, class? Now, when you do that, if both of these signals, let's say there's, we don't have to worry about any time difference. Like when you send a radar pulse and it hits and comes back, there's a time difference between when the first signal started and when you get the reception. So we'll cover that in a second. But if you look at this, and we look at the output of these things, the y of t, right here, we know there'll be cases. We know it's equal from 0 to t of basically just a squared, because it's going to be this times this in the overlapped area right here. So it's basically this and this, because you've got to do point by point multiplication, integrate it, and it would be d lambda. So that's going to be equal to simply a squared t, and that's true for t greater than 0, less than cap t. Y'all follow me on that, class? So basically, as this pulse is moving through, when t equals cap t, then the two pulses overlap. Do y'all follow me, class? And remember, the key is, I'm doing convolution. I took the input signal and I simply time reversed it and then shifted it. If it was correlation, if we just correlated the two, not convolved, I wouldn't write h of t. I'd just say you take whatever the signal is input, and you're going to use that signal and correlate it against the input signal, but with a time delay. Do y'all follow me? Because that's exactly what we're doing here. If you take a look at it, that's true. Now what happens for y of t when it's greater than cap t? Well, it would go from whatever the lower limit is, where now this thing's going to move through, and I hope you can see this. If it moves through like this, now this point is t minus cap t, and this is still going to be cap t. So the overlapped area would be from t minus cap t to t. Do y'all follow me, class? You're basically going to integrate over this window, and you still have a times a. So now I get a squared, and you'd integrate from t minus cap t to cap t d lambda, and this is still going to be a squared, and then you're going to get cap t minus the quantity t minus cap t, and that will be equal to a squared times 2t minus t, and that's going to be for t, small t greater than t, less than 2t, and then it's 0 else. Are you all with me on this basic convolution? Just a simple review. Okay, now what does that look like? That'll put over there. And it's 0 anytime else. Here's what it looks like. Remember, there's no time delay between the input pulse, the input pulse basically starts at t equals 0. So the actual value y of t, the output, with that match filter would look like this. And this would be a cap t. Right there. Y'all follow me? Now, the thing about that is, and you'll notice this, as this pulse moves through at cap t, it's the maximum possible area that you can get from the convolution of the two pulses, because the entire pulse is just represented down here. So it would basically be x of t squared that you're integrating over the time that it exists. Do y'all follow me? That's the most possible power you can get in the signal. But the most possible power only happens at one instant in time for this one. And that is cap t, right there. And this would be a squared, like just do it. At cap t, you're going to get a squared times t. And that's really the height squared times the width of the pulse. Y'all follow me in this class? Now that's the idea of a match filter. Whatever, you have to know, and with radar we do, whatever we're transmitting, we're going to take that signal and simply flip it. And we're going to use that signal in an autocorrelation function, because that's exactly, it's a cross-correlation function with the input, or with the received signal, and whenever that's a maximum, we plot it in time. Wherever it's a maximum, we know that time delay has to do to the distance with target. That time delay, if you take that time delay times the velocity of light, now you get the total round trip distance, you divide by 2, now you get the distance to the target. That's the whole idea. It's a real basic idea, but you've got to see it. And this match filter proof he does is not the best way to do it. It's normally done, at least in radar, we do it in the frequency domain, but I'm sticking with this one. Now, that what I just showed you is the essence of it. But if you get a time delay, and that's where, maybe I just should show you the actual, without all the math, just show you what I'm talking about. And we can do this just simply with cross-correlation, because a match filter is cross-correlation of the transmitted and input and received signal. That's all it is. As a matter of fact, in a lot of ways, I think it's easier to understand that. So if you take a standard radar system, I'm going to do it here, where you transmit a pulse, and you have an object out here, target. Pulse comes out, let's say this thing is at some distance or at some range R. Pulse comes out, hits, comes back and is received. So the transmitted signal, I'm going to say is this, and this is called the baseband signal. I'm going to transmit this. Let me make it a little different. I'm going to transmit this. This would be my sense signal. We'll call it X of t. Follow me? Now I listen, and the signal goes out and comes back. This is X of t. Here's what I receive. This is often called the transmitted signal, so it would be X of t of t. Then this is going to be what's received back of t. And what that's going to be is basically that signal, only it's going to be delayed by distance t, or time t, and then it's just going to repeat itself. You're going to get a replica of that, basically. Height A, this is t, O. Let me not use t here. I'll call it small tr. And so this point in time here would be small tr plus cap t, the width of the pulse. You're going to receive that. Now, if you take a look at this and you did an autocorrelation function, it's the same thing as taking this transmitted signal, right? Flipping it, creating h of t, and then using that for convolution, because ultimately you got to flip it back to do convolution. Do y'all follow me, class? So if we did an autocorrelation system, we want basically the autocorrelation sent and received signal, so that would be R of x transmitted, x received of tau. That's the expected value of the sent signal, which is x transmitted of t times the received signal, and it's going to be x received, and it would be, and here you're going to have t plus tau. If you're going to do cross correlation, you have to add that tau. Y'all follow me? Now, I'll talk my way through that. If you look at this, the only time this expected value has a non-zero value is if, since that's the receive signal and this is the transmit signal, we'll do it this way. I'll put receive signal here, transmit signal here. It'll be easier to see. So leave that as the receive signal, right? And if you take a look at this, if tau is 0 on the transmit signal, this is what's transmitted, here's what's received. There is no overlap. If you look at the two, point-by-point multiplication, it's 0 here times these values, and it's 0 there times these values, no overlap. But as this pulse moves this way, then all of a sudden, when the leading edge T right here hits this point, there begins to be overlap. Y'all follow me on that? Now the autocorrelation function is going to have a non-zero value. If you plot it, it does this. And the way I did it is a ramp function there. So you end up getting something that's called a shark fin. If you look out here and you talk about this function, which is the same thing as putting it through a matched filter with a time delay, you get R here of xt and x received of tau. It'll look like this. Right at the point where it would be TR, then it's going to start going up, and it's going to go up very quickly, peak here, and then it's going to have a shark fin look. And this right here would be at that T receive point. Then the peak right here would be at T receive plus cap T. And this point where it finally is extinguished is going to be T receive plus 2T. That's the essence of it. When you do the math on this one, for this, it's an autocorrelation. It's the same thing as taking the matched, doing a matched filter thing and taking this signal right here. Mathematically, you would write an equation for that. It's a simple one. By the way, it's just simply going to be equal to whatever the slope of that line is. So it would be A over capital T times T. You're going to take that signal, you're going to time reverse it. So it's A times cap T, or times T over cap T, and then you negate it, so it'd be a minus sign there, and then you're going to take that and add lambda to it and start moving it through. But this is the kind of stuff you see, and that will, and also because the noise is uncorrelated, all the noise in these things goes away. By the way, what I showed you here, normally with radar, just to be clear about this, that would be an envelope of the magnitude of the radar signal. You actually would get a whole lot of hertz. Like you would basically have a ton of periods of the actual waveform. Usually your radar is typically gigahertz, 9 gigahertz, 10 gigahertz, 20 gigahertz, something like that. And the windows are usually milliseconds to hundreds of microseconds. That means there's, if you think about that, there's about 1 million cycles typically in a radar pulse. So That way they can transmit it with an antenna designed to transmit the high frequency. This right here, what I'm showing you, is called a baseband envelope. And in the real world, when you do this, the first time you ever do this kind of stuff, it kind of opens your eyes that this stuff really works. When you actually do this, you transmit a radar signal. You have a digital record of what was transmitted in the baseband, not the high frequency component, because that's too much data. So they get a digital record of this. This is what I transmit if it was one pulse. I have that, and I listen for a return. And as soon as I start getting a return, I start recording that return until it's extinguished, and I know the time delay. Then I take that return, and I strip off the high frequency. You put it through, you know how to do demodulation, right? And you've had, you haven't. You had your radio lab, but you haven't had how to demodulate FM. You know how to do it with AM. Basically, you have to have a very stable local oscillator, and you multiply the received signal by the local oscillator frequency, and you get sum and difference frequencies. Mm-hmm. And you simply are going to take the sum frequency typically. You can do it, there's other ways to do this. You can use rectifiers and stuff like this. Anyway, when you ultimately strip off the high frequency component and get it, that goes from A to D. Now, when you do correlation, or we're doing autocorrelation, the whole thing is the only thing I'm going to do, I knew what I sent. So I have this information. And I take that, you can do it in the time or frequency domain. I take that information, and the only thing I'm going to do is very quickly just start time shifting this over there, point by point multiplication all the way down there, and do the equivalent summation, not integration, in the actual digital domain. Take that information and then plot it like this. Now in a computer, you don't see plots like this unless you ask for it. And then, lo and behold, it'll find out where that the autocorrelations function is a maximum. It'll find this. And from that point, when it knows that, I know that that time is associated with 2 times the distance. So I know that TR times the velocity of light, because that would be the distance traveled, would be the round trip, and I divide it by 2. And lo and behold, that's the range to the target. It's the centroid of the target. Because sometimes, I'm just throwing this out there so at least you appreciate some of the difficulty with radar. If you have a squadron of planes flying at you, if they're real far away, they look like a blob. You can't differentiate. As they get closer and they get more spread, you're going to get multiple returns that never ever completely die out, so you get like a ripple. You know what you transmit when you do an autocorrelation of that, you will see a maximum value, and that would be the centroid of that group of planes, or whatever it is up there. There's a whole lot more to this. I'm going to throw this out here. I'm just trying to give you a little more information. So that's one pulse, right? In real world, they don't send one pulse. They send that pulse, and then they send another pulse, then they send another pulse, and they'll send n pulses in a certain time interval. So it's basically a repetitive goes out, and then they listen for the echo from that. Now, because there are multiple pulses, each time you take a pulse and send it, if you have a data record of that and you use an autocorrelation function, then the signal to noise ratio goes up by the factor of n that you transmitted, the number of pulses. And it's similar to having just one very long pulse, but the problem with that is a very long pulse will not give you any information about 2 targets separated at a short distance. You'll just get you won't be able to tell anything between the difference. So they send multiple short pulses, and they'll do something, and that's called coherent processing. When they take a whole bunch of pulses, do a time reversal, and then correlate them, or basically use a correlation with what's transmitted and what's received. And what's amazing is how you can send a signal, and you're collecting, so this is something else I didn't get into. As you're collecting data, you can't even see the signal. So what you have to do is take segments of everything during the listening period and run fast autocorrelators or cross correlators on it to see if there's any information in there. And even though if you're looking at just the standard measurement on an oscilloscope, you can't see anything, As soon as you do that cross correlation, it becomes apparent that there's a signal there that you sent. That's really important to know, because you can pull signal out of noise doing that. I spent a lot of time with that. Now, he does talk about this in that section. And I'm going to ask you to do exercise 9-5-1 and 9-5-2 for homework on page 401. A good question you might have is, what are we responsible for on a quiz Friday? Possibly. Well, the autocorrelation function is something, or cross-correlation function, I should say, and autocorrelation function, or something I expect you to I mean, if you did the problems, you got a handle on it. Hopefully you did. But here's the kind of problem I expect you to be able to do. Actually, in the book, yeah. So in exercise 9-5.1, it gives you simply a signal. He says the transmitted signal, or the signal, S of t, is 1.5, and it's going to be times u of t minus u of t minus 1. And are you looking for it? It's way up, I think, up around page 400. It's on page 401, actually. And he says white noise has a spectral intensity of 0.15 volts squared per hertz. So then he asks for the smallest value of T0, which will yield the maximum output. What he's really saying, in time, where would the maximum be if we did autocorrelation of the transmit and receive signal? Y'all with me on this? So here's what it comes down to. If you look at this, just take a look at it for a second. What does it look like? Isn't that, I mean, you should be able to deduce this. This has basically got a value of 1.5, this signal, and this would be the transmitted signal, S of t, versus time. Y'all follow me on this, guys? Now, if you're going to match filter, you know you're going to do one thing. You're going to take that signal. I'm going to leave that one alone, and I'll put it as S of lambda here. This is lambda, and this has 1.5. Now, if it's a matched filter, my filter, H of lambda, is simply going to be equal to S, and it would be of T minus lambda, or he likes T naught, so I'll go T naught minus lambda. You with me, class? Y'all follow me? All right, so what does that look like? Well, it's simply this flipped. And this becomes T naught. And this would be T naught minus 1. Can you all follow me? The height of this is 1.5. But you understand what he's asking. It's not bad. Y'all with me? Now the output is going to be what? It's going to be this times this integrated, correct, class? It's basically point by point. Take point, 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 point. On all the overlap, you multiply them, and then you integrate it, correct? So what is that going to look like? Well, I think I actually did that earlier. And it'll look like this. On the output, and I'll put it here, I'll use S0 t because he likes that. The output itself is going to be equal to the integral from 0 to my t0 of simply 1.5 squared, because they're both flat pulses. It'll be simply d lambda, and that's going to be 1.5 squared times t0, and that's good from t0 greater than 0, less than 1. And then the output, S naught t here, is going to be equal to the integral from t naught minus 1 to 1 of 1.5 squared d lambda. And that's still going to be 1.5 squared. And here, it's going to be 1 minus t naught, or actually 2 minus t naught, and that's true for t naught greater than 1, less than 2, and 0 else. Y'all with me, class? That's what I had up earlier, right? Same exact thing. So plot it. What does it look like? Looks like this. And this would be t naught here. And you can see when t naught, or I should say, yeah, this is versus t naught. When t naught equals 1 second, you get the greatest possible value. Can you all see that? Right? I mean, here's the whole thing. We're doing convolution of 2 signals. There's no time skew. Y'all follow me on this class? If you do that, where's this thing going to be a max? Dead center of the convolution. As a matter of fact, the width of this is going to be 2 seconds, because if you can evolve 2 time-limited pulses, the total width of the result of the convolution of the two will be the sum of the first and the second. It's just the way it is. The max value for any kind of a square pulse like that, anything like that, will be right dead center in the middle. And that, where that occurs is when this exactly overlaps that. And by the way, it doesn't matter what the shape of this pulse is. This is a nice thing. Because if you think about this for a second, if I transmitted any shape, for instance, if I transmitted a shape that looks like this, then if I flipped and shifted the thing, what I'm going to get is basically this pulse, that pulse itself, a replica shifted like this. You all with me? And the point where you get the greatest the greatest integration of the overlap will be when this pulse is literally right there, and that will occur at the width of the first one. Can you all see that? It doesn't matter what the shape of that one is. It will always happen that way. If you have, think of a wacky one. Suppose you have a signature thing like, right? You flip it and shift it, you get the same exact signature here, and when that thing comes and overlaps exact top, you're going to get the maximum area. Now there are things called, I gotta say one other thing. This is real simple stuff I'm showing you. But in the real world, here's what happens. It's transmitted and received. They'll do things, one of them's a Barker code, and this I'm familiar with. So what they transmit with a Barker code is something like this. It's going to have negative and positive values. And they're a bit random. So this might be A, this is minus A, right? So if you take that code, flip it and shift it, basically it comes over here. It's really going to just take this code and move it here. And as it moves through, and you do the point-by-point integration, it's almost zero all the time until they exactly overlay, and then it just shoots up like crazy. That's used a lot of time because it is a higher resolve of the actual point in time where there's the correlation's the maximum of the two functions. Make sense? Okay, spent a lot of time thinking about that. But what's the next part? For that problem, it says for the value t0, find the value of the match filter impulse response at t equals 0, 0, 1, and 2. Now the only thing you're doing here is, for that problem, y'all see what, we basically had this function, right? For a time delay of 0, there's no overlap at 0. Can you see that? Mm-hmm. Time delay of 1, maximum overlap, that value would be what? It would be the height 1.5 squared times the width, 1, right? So 1.5 squared. Are you with me, class? Then he said for 2. At 2, it goes to 0 again. Y'all see that? And I think he asked, he says something like that. Let me just see how it goes. It's 1 point. Oh, I'm sorry, the width of that pulse is 2. So it would be 1.5 squared times 2, that's 5, isn't it? I think so. See, the width of the pulse in exercise 9-5.1 is, it goes from 0 to 2 seconds. So if you think about that, you can take 1.5 and square it, that's what, 2.25?
Then times 2 is 4.5.
He has 5, it should be 4.5. And
And the signal, the 1.5 is also multiplied by 2.
oh, I'm sorry. So it's actually a ramp. Let me go back to this. You should be able to see this easily though. It goes out to 2. Let me sketch it right here. And I'll try to recover from my error. Here's the actual signal he's sending. So it's saying my transmitted signal is going to be 1.5 times t times u of t minus u of t minus 2. So that looks like this. It's linear. The height of this at 2 would be 2 times 1.5 here, or it's going to have a height of 3. Sorry about that. Now, if you think about that as the transmitted signal, you're doing the correlation on it, right? You basically just take this whole signal. Don't worry about writing h of t as minus that and then flip and shift it. But if you look at this, what actually happened? You're taking that signal and you're just time skewing it, right? So if they ask the value where it's maximum, it would be at 2 seconds, total overlap. You all see that? And then it's basically, you're going to have to write an equation for this line right here as it moves and do it. Then he asks the value at time
0, 1, 0.
All right, at 0, it's 0. Everybody should see at 0 this pulse right here. This is time, t, and this is going to be t minus 2. At 0, right here, there's no overlap. It's 0. At times what?
1.
At 1, now this thing's going to be here, and if you look at this leading edge, if it's here, it looks like this. So now you have to write an equation for this line as a function of t and multiply it by an equation of this line and integrate from there to there. You with me? We could do that in a second, but I want to make sure you see the idea. With me? Then he asks at 2. At 2, the entire thing's overlapped, right? So at 2, when time equals 2, then you're going to get the integral from 0 to 2 of 1.5 t squared dt, and really we could put a lambda there, but it's the same idea because it's a dummy variable. So I get 1.5 squared t squared integrated is t cubed over 3. So you get 2 cubed over 3. Oh boy. So you got 2 times 1, 3 squared is 9 times 2 over 3, so 9 divided by 3. 6, not 5.
Mm-hmm.
Oh,
That's what I got.
that's probably the wrong answer. I'll double check that one. But that's basically the idea for the match filter. It's simply, you can think of it as just taking H of T as minus whatever you transmit T. You got to put a capital T in there, minus tau, and then you start shifting through there. Or T, he uses T0 as that front point. And that's it. Let's see what else he's got here. Sorry. He wants signal to noise in the, find the maximum signal to noise ratio. And so if the noise power was 1.5 V squared, right? So it would be 2 over 1.5 V squared. Or 0.15 V squared. Wait a second, 0.15. I gotta check that one. That doesn't seem right at all. That second part. All right, now, spent a lot of time with that. I'll put the solutions up for that exercise and the following exercise. And then the other thing I want to mention about is the, in section 6.8. The one with the diode, did you look at the solution for that I put up? Did you understand? I mean, the whole lot, I just wanted to mention a few things about it, because this is something, I mean, obviously both of these things we're talking about today, the whole idea of a match filter, it is really a cross-correlation function. And if you use the transfer, or the impulse response is just equal to the time reversal of the transmitted signal with the time skew, then that's the match filter. And the match filter has an optimal value when the two pulses are exactly overlaying each other in time. But for this one with the diode, this one, it's an ideal diode, but it's a little tricky. So he's saying this is the input signal. He's got a resistor R, then he's got a diode, then he's got a resistor R here, and this is the output. And for the input, for X of T, this is a random variable. And it has possible values of plus, I think it's 12 and minus 12, right? And he has, if you take a look at this, he's saying that this signal is something it comes and it flips, maybe the same here, but it's only related, or I should say the autocorrelation function is something that has a value TA where that's the maximum, basically it is correlated within that. I'm trying to think of the exact words he uses here, but he says yeah, he's saying T, he just states TA is 0.1. That is the time limit of any kind of relationship or correlation for these functions. For this one, the autocorrelation function of this is simply going to be the 12 squared. It's always the magnitude of this. If you get a positive and negative pulse like this, and if you do this, you know, if you wanted the definition of this, I'll write it down in a second, but it does work out. Then it's going to be 1 minus, and it would be magnitude of T over TA. Has to be symmetric. And that's the autocorrelation function if T, magnitude of T, is less than or equal to TA, and it's 0 else. And by definition, the autocorrelation function is the expected value of x of t times x of t plus tau. Here's what I have to be careful. I want to make sure. Now, these two have a correlation that's not 0 as long as that value tau doesn't exceed TA. If it goes beyond TA, they become independent. They're uncorrelated. So it'd be just the expected value of the first function times the expected value of the second function. You hear me? Just listen, please listen to this. Now, anytime that value is greater than TA, here's what actually happens. You're looking at the expected value of x times the expected value of x plus tau. Well, the expected value of this function, if you look in the chapter, is 0. You all see it's plus to minus 12. The expected value or average value is 0. So it's 0 beyond that point. Now, why does it look like this? The easiest way to see this, in my opinion, think about two pulses. Here's the first pulse. It has a value of 12. And here's the second pulse, but it's skewed by TA. So the second pulse is going to be this. Here's the interval that I actually want the average value over. Well, you can take a look at this. I'm leaving them both as plus, but it's saying if they're in the same interval, it's literally that waveform skewed. That's all it is. There's no change in the actual values. If you look at this, basically you can see this is the overlap area here. And that overlapped area goes to 0 when this, call it TA, call it T. This should be TA here. When that value T approaches TA, it goes to 0. That's probably the easiest way to think about it. There's a lot more involved in here because they make this random, where this can be anywhere and this can be anywhere plus that time skew. Now, that works, and if both are negative, well, you get negative times negative is positive. You with me on this, class? And then anytime, I mean, this waveform and this waveform are replicas of one another for this thing, because it's basically the time, it doesn't change, the state doesn't change within a value of TA. I wish I said this a little better, but that's the idea, and that's how come this works, because it's exactly what I'm trying to show you there, the overlapped area. Now, when you take a look at the diode itself, here's where it gets tricky. Give me 1 more minute or 2 more minutes at most. I'll try. When you get the diode output, if this is a square wave here, it was going like so, from minus or plus 12 to minus 12 here, and such, the output is only going to be positive because of the way I've drawn the diode. You follow me? And well, since these two resistors are exactly the same, Y of t itself will have a maximum voltage of 6 and a minimum voltage of 0 when it's reverse biased in the diode. And it would look something like this. Something like that. Now, everybody okay with that? And here's the deal, when I take the expected value for y here, Ry of tau is the expected value of y of t times y of t plus tau. If they're in the same, and this gets a little crazy, if you take a look at this, assuming, and statistically speaking, 50% of the time the pulse is on, 50% of the time it's off. Over here, the pulse is always on, but its value is either plus or minus 12. Over here, 50% of the time it's on. So when you do this autocorrelation here, if you take a look at this, for these two to be, or if you multiply them and they have a magnitude of 36, is the possible magnitude. Now, of that would only occur 1/2 the time, and you would, yeah, exactly, you would have 1/2 the time. During that time, 1/2 the time, now you're going to get something where you're going to have this type of, it'll be basically the same 1 minus the magnitude of t. It's going to be that same taper over TA here, but then that's true as long as t is greater than 0, or I mean tau, sorry, I put t here, it should be tau. As long as tau is greater than 0 and less than TA, but then outside their range, so if you look at this, once tau is greater than that, and I can say for tau greater than TA, now the expected value of x of tau times, or x, I'm sorry, y, pardon me, y of t times y of t plus tau here. Now these are mutually independent. It's the expected value of y of t times the expected value of y of t plus tau. And because they're mutually independent, that value is the expected value of the pulse. And that's 3 here, and the expected value of this pulse is 3. It's really going to be half of 6. Because 6 value, it's going to be 6 volts half the time, 0 volts the other half. Can you follow me? Now that means, if that's the case, you get 9. So out here, the autocorrelation is 9 when tau is greater than TA, and it never goes to 0. Are you with me on this? Follow me? You can express this a lot of different ways. If you take this one right here, you can break that up and you can have 18 minus, and it would be tau over t, and wait a second, I'm sorry. This would only occur a quarter of the time. And the reason is, yeah, my bad on that. Because here's the possibilities. You could have x of t plus, this would be like the x version of t would be plus, and you could have x of t plus tau positive as well. Those are both positive for this. And the output here, if they're both positive, would have values. But then you can have x of t equal plus and x of t plus tau be minus, or you could have a minus plus or 2 minuses, and only 1/4 of those possibilities give an output that's non-zero. And now, so that's going to be actually that plus 1/4 there. Anyway, if you take a look at the answer to that in the solutions manual, it'll make, or in the solutions I posted, it'll make sense. But that particular problem, yeah, he has the right answer down there. But then he asks for a cross correlation. Here's the bottom line on this stuff. I'm not gonna ask you a question about cross correlation for any problem at that level of complexity. But if I ask you for autocorrelation or for anything with matched filters, input-output relationships, I'll give you a few problems in there. I'd expect it. The first problem in exercise 6-8.1 and the problems I assigned at the back of the chapter, those are legitimate for section 6-8. Follow me? For the quiz Friday. Did you look at the problems in 6-8 in that section in the back or not? Did you? All right, they're not that hard, but if you don't do them and spend a lot of time concentrating on them, you can mess up. I won't throw a diode at you, because that kind of, it can cause you some problems. All right, I'll give you some more problems and I'll see you Friday. I had to get the match filters today, and I don't feel I did that good a job, but, yeah.
Are we gonna say power spectral density, by chance?
Well, yeah, I mean, it's almost implicit if you're gonna, and I'll be fair about it. If you need transforms, I'll give you a table if you need transforms. Because I think you do in chapter 7, the stuff on power spectral density. Do you need the Fourier transforms? So I'll give it to you. All right. See you Friday for the wrap up. Here's my plans beside the quiz. I'll take first questions. Any questions you have at the beginning of class about anything. Remember, the final is comprehensive. We've done a lot. If you look back, conditional probability, expected value, variance, we did Gaussian, Rayleigh. Think about all the stuff we've covered. It's a fair amount of breadth, but I'll give you tips on stuff. And our final is when again?
The Friday.
Next Friday at 8 a.m.
Yep.
Boy, that's the worst possible time. Friday at 8 a.m. I would rather have a final at like at 12 or 1 o'clock on a Wednesday than I would at 8 o'clock on a Friday, in my opinion. But is that the last day of finals? Friday at 8. Not what I was dreaming of.
I have to move out like right after it.
What?
I have to move out right after the final.
You're evicted? Are they still those leases where you don't even stay through graduation, you gotta leave?
Yeah,
before-
mine was over like, what is the date? The 30th or the 29th? 29th? Yeah, mine was over 9 days ago.
Mine is today. I gotta move out today.
Well, I could have like.
Can they give you a
asked my-
grace period or not?
They really don't. unless
Alien
you, like,
management is
own the
evil.
place.
Well, I know the landlord, so I had asked to extend